Welcome all for the video tutorial on machine learning, and today we'll continue with our fourth module. And the fourth module we are going to discuss about the fifth session, which is about MDL principle. So what is MDL? MDL is nothing but minimum description length principle. Okay, what is actually this is? It is a principle which is used as a powerful method for inductive inference and for a basis of statistical modeling and for a pattern recognition and in machine learning. And it is going to explain the principles, what is involved when you have limited set of observed data and when you need a greatest compression of data. And this is probably suited for dealing with model selection, prediction and estimation problems in situation where the model under consideration can have a complex and overfitting of data as a serious concern. In MDL, we are going to design a code for transmitting a message, okay, and we are going to transmit a message which has been drawn at a random. We are going to draw a message randomly and we are going to transmit that message, and we specify that message as I, and the transmission, the probability of transmission, we specify it as Pi. Okay, and your message length depends upon the number of bits required to encode your message. Okay, what is the need of encoding the message here? Here, for a purpose of security constraints, we implement the encoding technique. So when you send the data has to be we are supposed to see that the data has been delivered, it has been sent and it has been delivered in a secured means. For that purpose, we are implementing the encoding concept with this. Okay, the main purpose of encoding technique is to have a security measures. Okay, and here it is this principle, the MDL principle, will give us a trading of hypothesis complexity for the number of errors committed by the hypothesis. So what are the errors that has been committed by the hypothesis? We'll be able to trade off that hypothesis, complexity of that hypothesis, by this MDL principle. Okay, now we'll see the derivation of MDM principle. Okay, so actually we have derived this MDL principle from HMAP, maximum of posterior hypothesis. Okay, from that we have derived this MDL principle. So from HMAP, what is the formula we have for HMAP? We know that HMAP has been derived as argument of max, H belongs to the capital H, probability of D given H multiplied with the probability of H. This is the general formula we have for HMAP, and we are going to derive minimum MDL from this equation. Okay, and we can express the same equation in terms of log. Okay, you can represent the same equation in terms of log, and we implement that through log. For only reason behind it is for simplification. For the sake of simplification, we introduce a logarithmic value. So when I introduce logarithmic value for the above equation, I get the equation as HMAP is equal to argument map or ARG max, H belongs to the capital H, log, introducing logarithmic value, so log 2 base 2 with that of the probability of D given H plus log 2 log base 2 into the probability of H. This is in terms of maximizing. You are introducing the logarithmic value in the maximizing concept. So it's the same thing. If you introduce with the minimizing concept, we are going to introduce the same logarithmic value with the minimizing concept with the negative value. So that is HMAP is equal to argument min, H belongs to capital H. Since it is negative, it is minimizing the negative, we are introducing minus, it is minus log to the base 2 probability of D given H minus log to the base 2 probability of H. From the above derived equation, we can rewrite the equation that is HMAP of hypothesis by writing it as sum of description length of the hypothesis and along with the description length of the data given with the hypothesis. That is, we are going to rewrite the equation into H map, which is equal to arc min, where H belongs to capital H, LC of H, LCH of H plus LC D given H of D given H. Okay, L is nothing but the length of the data, the size of the data. Okay, and CH and CD are the encoding techniques that we have used for H and D. So what is the encoding technique? Optimal encoding technique we have used for the data sets H and D. What is the need for implementing the encoding technique here? The need is, for the sake of security concerns. For the reason of security, we are using this technique. So MDL equation is derived as MDL, hypothesis of MDL, that is hypothesis of minimum description length is equal to the R min of H belongs to the capital H, and the length LC1, that is the length of C1 of H plus length LC2 of D given H. Okay, and LC of X is nothing but the length of the data what we have chosen. Okay, what is the data we have chosen? That is what it has been specified as. LC of X is the description length of X under encoding C. We have chosen the encoding technique for the security concern. Okay, and they are given one example here. H is the decision tree and D is the training data, and we have the length of C1 of H and we have length of C2 of H, that is D given H. Okay, now if length of C2 of D given H is 0, if that example what we have classified as perfectly by H, and we derive the minimum description length by substituting that in the above equation what we have derived for the minimum length principle. See, MDL is also derived from the information theory, where in that way we know what is the formula for H map. H map is given by argument of max, H tends to the capital H, the probability of D given H multiplied with the probability of H. Now for the sake of simplification, we introduce a logarithmic value. So when we introduce the logarithmic value, we for a maximum hypothesis, we specify it as argument or ARG max, H belongs to the capital H, log to the base 2 probability of D given H plus log to the probability of H. This is in the case of maximum hypothesis, maximum priority hypothesis, and in case of minimum, and when you need to minimize it, we introduce an negative value for that. So we rewrite it as argument min H belongs to the capital H minus log to the base the probability of D given H minus log to the P of H. Okay, and we have derived this from the information theory, and we do this for selecting our shortest coding length. Okay, why we do this? Since it is minimum description length principle, we are in need of choosing the shortest coding length, so that you have an minimum, you can, the hypothesis what you derive, you can have a maximum hypothesis, maximum posterior hypothesis with the minimum length. With the minimum path, you will be able to obtain your maximum posterior hypothesis. When we equate both the equation hypothesis of H map and HMDL, both is going to give you detect the same output. So hence therefore H map is equal to, that is hypothesis of maximum posterior priority is equal to the hypothesis of minimum description length. Both are same here. Final outcome of minimum description length is your H map is equal to MDL. Okay, this is what, okay, your maximum posterior hypothesis is equal to the hypothesis of minimum description length. When you derive it, we get both outputs are same. So both H map is equal to hypothesis of MDL. Okay, thank you all.